Welcome to the deep dive. So our usual mission here is to take one massive, complicated subject, a war, an economic theory, a huge slice of history, and spend the whole time just tearing it down to its essentials.
Right.
But today, we're doing something a little different. We're not going deep on a single topic.
Exactly. Today's what we're calling a brain binge. So instead of tunneling down into one thing, we are going to take this rapid fire tour across, well, the most bizarre, curious, and genuinely mind-bending facts about reality we could find.
And we really did find them. We've pulled together over 100 of these little cognitive nuggets from all our sources. And the mission for you, our listener, is pretty simple. We want to give you the ultimate shortcut to feeling incredibly well-informed, but maybe also a little unsettled by the sheer strangeness of the universe you live in.
I think unsettled is a good word for it. The central theme here really is that reality just defies intuition.
Oh, completely. Common
Common sense fails spectacularly when you start dealing with extreme time, extreme density, or, the extreme complexity of life. So this is all about celebrating those aha moments where science pulls back the curtain and shows us that everything is way more dynamic, more interconnected, and just downright bizarre than we usually think.
I love that.
Yeah.
And to handle this intellectual overload, we've organized all these facts into 6 thematic chapters. We're starting at the absolute biggest scale possible.
You have to start with space.
We have to start with space. We're going from the cosmos all the way down to the quantum, all in one sitting.
So let's begin this journey at the cosmic scale. This is where time is flexible, density is, frankly, terrifying, and the only constant is immense, staggering distance.
Prepare to feel very, very small. Okay, so when we start talking about the universe, the biggest hurdle is always scale, right? Translating numbers our brains can handle into numbers that describe, I don't know, the distance between galaxies.
Yeah, our brains just aren't wired for it. Billions of light years.
Yeah.
Billions of years. It's just noise.
Exactly.
Which is why we're starting with the most manageable measure of cosmic time we have. And it's actually right here in our own solar system. We call it the solar lag.
Okay, tell us about this 8-minute delay. So if the sun just vanished, we wouldn't know right away.
Not at all. That's the gap in all human knowledge about our closest star. If at this exact moment the sun were to just pop out of existence,
Gone.
we would have no idea for about 8 minutes and 20 seconds. That's how long it takes for the last little bit of its light and, crucially, its gravitational information to travel the 150 million kilometers to reach us.
8 minutes of just blissful solar-powered ignorance.
Pretty much.
But that's a tiny, tiny window. It really drives home the fact that everything we see is a historical record, even in our own cosmic backyard.
It's the perfect analogy for the entire universe. When you look up at the night sky, you are always seeing the past.
Always.
You look at a star that's, say, 10,000 light years away, you're seeing it as it was 10,000 years ago.
So for all we know, that star could already be gone.
It could have exploded millennia ago, but its light is still on this relentless journey to your eye. It's like a slow cosmic echo of something that no longer exists. It just adds this profound layer of history to everything you see.
And when you start comparing those time lags to physical scale, I mean, that's when things get truly impossible to visualize. The number of stars in the observable universe is one of those facts that just, it breaks your brain.
It really does. The classic analogy, which still somehow undersells the reality, is this. There are more stars in the observable universe than there are grains of sand on all the beaches on Earth.
I remember reading that even that comparison isn't really close, is it? The stars actually outnumber the sand by a lot.
Oh, by many orders of magnitude. It's an extreme difference. Current estimates put the number of stars at around 10 to the power of 24. That's a septillion.
I can't even picture that number.
Nobody can. And trying to count every grain of sand on every coast, every island, every desert, you end up with a much, much smaller number. It's the ultimate contrast between the vastness out there and the, limited scale of our home.
But all that vastness doesn't mean it's static. We think of the stars as fixed points of light, but in about 4 billion years, there's going to be a seriously violent, slow-motion merger happening right where we live.
We are talking about the coming gravitational embrace between our Milky Way and the colossal Andromeda Galaxy.
Right, they're heading for each other.
Yep, at about 110 kilometers per second. They're on a collision course, and will start to merge in about 4 billion years.
And the resulting galaxy even has a nickname already, right?
It does. Milkomeda.
Milkomeda.
Yeah.
That sounds terrifying. What happens to our solar system when two massive galaxies just smash into each other?
Well, that's the fascinating part. Because the distances between stars are so immense, actual stellar collisions are, well, they're highly unlikely.
So we probably won't hit anything.
Probably not. But the gravitational forces will be enormous. They'll completely restructure our galactic neighborhood. Our solar system will almost certainly be flung into a dramatically new orbit, maybe much further from the new galactic core.
So our night sky would look completely different.
Completely unrecognizable. Over those 2 billion years of merging, you'd see the massive distorted shape of Andromeda just gradually taking over your entire field of view until eventually the two spirals settle into a new, single, enormous elliptical galaxy.
And while that collision is happening slowly in the distant future, cosmic violence is. I mean, it's happening every single second right now.
It's instantaneous and it's catastrophic. Every second, somewhere in the universe, a star explodes as a supernova.
Every single second.
These events are the final cataclysmic end for massive stars. And they're so energetic that they briefly outshine their entire galaxies.
Outshining hundreds of billions of other stars combined.
Exactly. It just shows how concentrated energy can completely dominate the light output of an enormous stellar population.
And the leftovers from those explosions, they create some of the most bizarre and dense objects we know of. Neutron stars.
Neutron stars are the ultimate example of extreme density. They're stellar corpses, just packed so tightly that their matter is almost entirely neutrons. They're only about, 10 to 20 kilometers across, but they have more mass than our sun.
Okay, so how do you even begin to explain that kind of density?
Yeah.
The teaspoon fact is what always gets me.
Right. So think about it this way. A single teaspoon of neutron star material
Just a teaspoon.
would weigh billions of tons here on Earth. That's more than the weight of every single cargo ship, every aircraft carrier, and every skyscraper in a huge city like New York, all combined,
Wow.
and compressed into a volume smaller than a grape. The gravity on its surface is so intense that if you drop something, it would hit the surface at about half the speed of light. It just shatters our intuition about what matter is.
And if the neutron star is the density champion, then the black hole is the champion of compression.
Absolutely. If you could somehow take our entire planet, Earth, and compress it down to the density you need to form an event horizon,
Okay.
it would fit into a sphere about 1.8 centimeters across.
That's smaller than a marble.
Smaller than a marble. That's the sheer amount of compression needed to create the ultimate gravitational trap. It really shows that gravity isn't just a gentle tug. It's the force that shapes space-time itself.
Okay, let's zoom back out a bit to our celestial neighborhood and talk about planetary anomalies, because even the planets right next door are just weird. I'm thinking about the diamond weather.
Ah, yes. The atmospheric physics of Jupiter and Saturn. Deep within their atmospheres, the pressure is so immense that it compresses carbon atoms into solid crystals.
It literally rains diamonds.
It may literally rain diamonds deep down in their atmospheres. This combination of intense heat and pressure could even lead to liquid carbon oceans surrounding a solid diamond core.
While it's raining diamonds on Saturn and Jupiter, Jupiter also has the immortal storm, the Great Red Spot.
Right. The Great Red Spot is a vortex. It's a gigantic, persistent storm that's larger than the entire Earth, and it's been raging for at least 300 years.
At least.
We only confirmed it 300 years ago, but it could be much older. It's this immense, self-sustaining atmospheric feature that just defies the normal laws that make storms on Earth dissipate.
And time itself just acts weirdly on our neighbors. Venus, for example.
Venus is infamous. Its rotation is so slow that a day on Venus, the time it takes to spin once, is actually longer than its year, the time it takes to go around the sun.
That's so counterintuitive.
And then you have Mercury, where a solar day from sunrise to sunrise lasts 176 Earth days, but its year is only 88 days long.
So it stays twice as long as its year.
Exactly. It just highlights that rotation and orbit are completely independent and sometimes bizarre factors.
And moving beyond the planets, most of the ordinary matter in the universe isn't actually clumped into stars and planets like we think.
Correct. Most of the ordinary matter, the stuff made of atoms, is in this thin, incredibly hot gas. It's spread out in these vast cosmic filaments that connect galaxies together in a kind of cosmic web.
So it's mostly invisible.
It's too diffuse and too hot to detect easily, but it's the vast majority of atomic matter just hanging out in the space between the shiny galaxies.
And a quick fun one for anyone who dreams of being an astronaut.
Yeah.
Life on the International Space Station.
Right. Astronauts on the ISS see 16 sunrises and 16 sunsets every single day.
16.
They orbit the Earth every 90 minutes. Imagine trying to keep a regular sleep schedule when you're constantly shifting between light and dark. It's a huge environmental challenge.
And finally, before we leave space,
Yeah.
we have to talk about the vacuum. The idea that even empty isn't really empty.
Well, we call it a vacuum, but according to quantum field theory, space is never truly empty.
It's full of energy.
It's a sea of energy. Every cubic centimeter of this supposed vacuum can contain hundreds of these ghostly virtual particles that just pop in and out of existence almost instantly. They borrow energy from the vacuum for a fraction of a second, and then they're gone.
A constant, furious, invisible fermenting of energy.
At the quantum level, yes.
All right, so we've covered the universe. Now let's bring it all the way back home. When you think about Earth, you think you know it. It's solid ground, it's familiar. But our world is just full of extremes of heat, depth, and bizarre hidden geography that rival anything we just talked about in space.
We can start with what's literally right under your feet. The Earth's core is a terrifying place.
Right. Its temperature is comparable to the surface of the sun.
Mm-hmm.
And the thing that always gets me is the distance. We're only separated from that incredible stellar heat by a few thousand kilometers of rock.
We're living on the thin, cool skin of an incredibly hot, dynamic planet.
That thin crust is our entire defense system.
Okay, now let's go the other way. Depth. The Challenger Deep, the deepest known point in our oceans. It really puts our understanding of scale into perspective.
How deep are we talking exactly?
So deep, it's nearly 11,000 meters. That if you took Mount Everest, the world's tallest mountain, and placed it on the seafloor there,
Oh, yeah.
its summit would still be more than a mile underwater. It's this hidden geographical expanse, bigger than all the visible mountains on land combined, just existing under crushing pressures.
And speaking of counterintuitive geography, the world's largest desert, most people would guess the Sahara.
And they'd be wrong. It's Antarctica.
Because a desert is defined by precipitation, not heat.
Exactly. Antarctica gets extremely little precipitation, less than 200 millimeters a year, which makes it technically the world's largest desert. A cold, icy desert, but a desert nonetheless.
And that extreme dryness, even in hot deserts like the Sahara, can preserve things across, geological time.
That's right. In parts of the Sahara, you can still see fossilized raindrop marks from millions of years ago.
No way.
Yes. The conditions are so dry and stable that this ephemeral evidence of ancient weather, just the impression of water hitting mud, has been preserved on the rock for eons. It's a physical photograph of the planet's ancient atmosphere.
We talk about deep time a lot, and the planet reminds us that even our days aren't fixed.
Not at all. Earth's rotation is gradually slowing down.
And that's because of the moon's gravity.
It's the constant tug of the moon's tidal pole, which creates friction. So the days are getting longer, but very, very slowly. We're talking a few milliseconds per century.
But it adds up.
It adds up over geological time. The rotation has slowed significantly over the planet's history. It's a reminder that nothing, not even the length of a day, is permanent.
And while our days are slowing down, what's happening under the waves is way more dynamic and mostly invisible to us.
About 90% of Earth's volcanoes are hidden under the oceans, and they're all connected by something called the mid-ocean ridge.
What's that?
It's a continuous belt of undersea mountains that's longer than all the continents put together. We focus on the land masses, but the single largest geological feature on our planet is this continuous volcanic underwater mountain chain that's constantly creating new crust.
And the ocean is also where we see some wild physics, like where two different bodies of water meet but don't mix.
Right, there are places where two oceans meet, and you can literally see a visible line between them. It's not a wall, obviously, but it's a sharp boundary.
What causes it?
It's caused by differences in temperature and salinity, which affects the water's density. So they don't mix easily. It's a stark visual of the planet's vast segmented fluid dynamics.
Okay, let's go back underground, but not to the core. Let's talk about the mysteries in caves, specifically those giant crystals.
Ah, yes. Some caves, like the ones in Mexico, contain crystals so large you could literally walk along them like translucent beams.
That sounds like something from a movie.
It does, but they're real, and they're not formed quickly. They grow over hundreds of thousands of years in hot, mineral-rich water. It just shows the incredible power of slow, perfect mineral deposition.
And sometimes even rivers can be layered.
Yes, there are rivers that literally run under other rivers in cave systems. You have a surface river, and then beneath it, in a dark tunnel Clear, fresh water is flowing in a totally separate current. It's a geographical oddity of nested systems.
And what about lakes that are like blood red or bright pink?
Those vibrant colors are usually from microscopic algae that are thriving in extremely salty or mineral-rich water. These organisms are often extremophiles, and they produce pigments like beta-carotene that give the water that shocking color. It's a sign of life adapting to conditions that would kill almost anything else.
We've talked about oceans, rivers, caves, but the most densely populated environment is right where we started, on the ground itself.
A single teaspoon of healthy soil can contain more living organisms, bacteria, fungi, protists, microinvertebrates, than there are human beings on the entire planet.
More than 8 billion organisms in a teaspoon.
It's a bustling, complex ecosystem that's absolutely critical to all life on Earth.
And that biological density connects directly to the climate. Take the Amazon rainforest, for example. It's not just passively sitting there getting rained on.
Not at all. The Amazon creates so much moisture through transpiration, that's water vapor released by the trees, that it actively helps trigger its own rainfall hundreds of miles away. It's a giant green engine for the atmosphere.
And the trees themselves aren't passive. They communicate in ways that sound like fantasy.
But it's scientific reality. Some trees release chemical signals into the air to warn their neighbors about pests.
Wow.
Or they use networks of symbiotic fungal threads in the soil, people call it the wood wide web, to share nutrients and alert each other to danger. It's a profound biological communication network that we're only just beginning to understand.
All right, we've covered the cosmic and the terrestrial. Now let's zoom in on life itself. The animal kingdom is just. It's full of incredible biodiversity and bizarre adaptations that make you question what's even possible for biological organisms.
Then we have to start with an animal that seems almost alien in its design, the octopus.
Octopuses are phenomenal. They have 3 hearts, and their blood is blue. Why is it blue?
It uses a copper-based protein called hemocyanin instead of the iron-based hemoglobin that we have.
Is that better?
It's actually less efficient overall, but it functions much better in extremely low oxygen, cold environments like the deep ocean. So it's a necessary trade-off. But what's even more bizarre is that each of their arms has a degree of independent thinking.
Decentralized intelligence.
Exactly. There are clusters of neurons in the arms that act like mini brains, so the arms can solve simple problems, open jars, and even taste things, all while the main brain is busy with something else.
That's amazing. And speaking of bizarre life cycles, we tend to think of aging as this inevitable process, but some creatures have figured out how to cheat death.
The immortal jellyfish, a certain species can, if it faces stress or injury, revert back to its younger polyp stage after reaching adulthood.
Oh, it just resets its life cycle.
It essentially resets, allowing it to potentially live forever as long as it isn't eaten or destroyed. It's a staggering example of biological plasticity.
But the ultimate survival award has to go to the water bears, right? The tardigrades.
Yeah.
These things are basically indestructible.
They are the benchmark for biological resilience. These tiny microanimals can survive being frozen, boiled, dried out for decades, intense radiation, and even the vacuum of space.
Ow.
They enter a state called cryptobiosis, where they suspend their metabolism almost entirely. They are the true ultimate survivors.
And they're not the only ones with a weird relationship with temperature. There are some frogs that have perfected controlled cryogenics.
Yes. Certain species of wood frogs literally freeze solid in the winter. Their heart stops completely. Their breathing ceases.
How do they not die?
They accumulate glucose in their organs, which acts as a cryoprotectant, protecting their cells from being destroyed by ice crystals. Then when spring comes, they just thaw out and hop away. It's a miracle of biological antifreeze.
Okay, now let's talk about the extremes of speed and power in tiny packages. The hummingbird and the pistol shrimp.
A hummingbird's heart can beat more than 1,000 times per minute when it's flying. That's a tremendous metabolic rate. But the pistol shrimp might be even more extreme.
This is the one with the claw.
Right. When it snaps its claw shut, it creates a tiny bubble through cavitation that then collapses violently.
And that collapse generates heat that's comparable to the surface of the sun, right?
Exactly. For a brief moment, it reaches temperatures of about 4,400 degrees Celsius. That heat is generated purely by mechanical force. It's incredible concentrated power in a tiny little crustacean.
Let's move to collective behavior and intelligence. The sophistication of social insects always amazes me, especially army ants.
Right, army ants. A single colony can contain hundreds of thousands of individuals, and they all act like one superorganism. When they need to cross a gap in the forest floor, they'll form living bridges with their own bodies.
They just link together.
They link together, sacrificing their individual position to ensure the collective structure survives and the colony can move forward.
And it's not just insects. Some plants show surprising levels of, like, basic computation.
The Venus flytrap is the classic example. It can count.
It can count.
It only closes its trap when its trigger hairs are touched twice within about 20 seconds. This calculation ensures it's dealing with a live insect and not just, a falling raindrop, so it doesn't waste the massive amount of energy it takes to close the trap.
Moving higher up the cognitive ladder,
Yeah.
animals exhibiting primate-level intelligence, but in unexpected places, like birds.
Crows are highly sophisticated. They can recognize individual human faces and remember people who treated them kindly or badly. They can hold grudges for years.
Wow.
And some parrots have been shown to understand the concept of zero as a quantity, which requires abstract thought.
And the emotional depth of some mammals is just profound.
Elephants, for example, they seem to recognize the bones of their own species. They'll often show interest in skulls and tusks, delicately examining them.
It's compared to mourning.
It's widely compared to mourning, yeah. It suggests a depth of awareness about death and kinship that we're only beginning to appreciate.
There's also that strange reciprocity in the animal kingdom, like the social contract of vampire bats.
Vampire bats share blood meals with unrelated hungry bats in their colony
Why would they do that?
because they operate on a debt system. They essentially keep track of who has helped them before. This system of social reciprocity is essential for their collective survival. It's like insurance against starvation.
Okay, let's end this section with some scale and food facts. We'll start with one of the only foods that seems to last forever. Honey.
Honey never really spoils. Archaeologists have found pots of honey in ancient Egyptian tombs that are thousands of years old and still technically edible.
And why is that?
It has a very low water content and high acidity, which prevents bacteria from growing. It's also a testament to incredible labor. A single spoonful of honey represents the entire lifetime's work of about a dozen bees.
That puts it in perspective.
Yeah.
On the flip side of time, we have unbelievable growth rates.
Some species of bamboo can grow more than a meter in a single day under the right conditions.
A meter a day. You could almost watch it grow.
You practically can. It demonstrates a biological speed that's just utterly foreign to us.
And the largest living structure on Earth. It isn't a single plant or animal, but a collective of tiny organisms.
The Great Barrier Reef. It's the largest living structure built by billions of tiny coral animals that deposit calcium carbonate skeletons over millennia. It is biological engineering on a planetary scale. You can see it from space.
And finally, the cultural phenomena of the deep ocean.
Whale songs. These complex songs can travel hundreds of kilometers through the ocean, and they change slowly over the years, almost like cultural fashions or dialect shifts.
So they learn from each other.
It demonstrates complex, shared knowledge being transmitted across massive distances and time frames by a non-human intelligence. It's beautiful.
We've traveled across space, through the Earth, and looked at other life forms. Now, let's turn the focus inward, to the physics, the chemistry, and the neurological tricks that make up your existence.
And we start with a really startling fact about identity. You are not just you. You are an ecosystem.
That's right. Your body contains more microbial cells, bacteria, fungi, archaea, than human cells by number.
More non-human than human.
By cell count, yes.
Mm-hmm.
We are fundamentally a walking collection of organisms, our personal microbiome, which is crucial for digestion, immunity, and even your mood.
And if we look even smaller, down at the atomic level, the whole concept of a solid body just dissolves. We are mostly empty space.
The atoms in your body are mostly empty space. If you could somehow remove all that emptiness, all the actual matter that makes up your body could fit into a volume far, far smaller than a single grain of rice.
Physically, we're almost all void.
Right. But if we're mostly empty space, why do I feel solid? Can you remind me of the physics of that?
What you feel as touch or solid isn't matter compressing against matter. It's the electromagnetic repulsion between the electron clouds of the atoms in your hand and the electron clouds of the object you're touching.
So you never really touch anything.
You never truly touch anything. You just feel the powerful force of resistance between atoms.
And yet, the little bit of matter we do have has this stunning cosmic history.
It's the ultimate mind bender. The calcium in your bones and the iron in your blood were forged inside ancient stars that exploded long before our sun even existed.
We are literally built from stardust.
From the remnants of supernovae.
And that star stuff isn't fixed. You are constantly in a state of flux. Millions of your cells die and are replaced every single second. Even your skeleton completely remodels itself over the course of several years.
Okay, now let's talk about the 3 pounds of thinking matter inside your skull. The brain. It's a huge energy hog.
It really is. The human brain is only about 2% of your body weight, but it uses around 20% of your resting energy. It's this hyper-efficient, high-demand biological machine running constant calculations even when you're asleep.
And those calculations aren't immediate. Your perception is always a little bit behind reality.
Right? Your perception is always slightly out of date. It takes tens of milliseconds for signals to travel from your eyes or ears to your brain to be processed. We are always living in the very, very recent past.
And the brain is a master at fabricating reality to smooth over the gaps, like with our blind spot.
Yeah, you have a built-in blind spot where the optic nerve exits each eye, but you never notice it.
Because your brain actively fills in the missing visual information based on the surrounding data and what it expects to see. It shows that we don't just see reality, our brain actively constructs a seamless internal model of it.
Which makes memory so fascinatingly unreliable. We think of memory as a video we can just replay.
It's the total opposite. When you remember an event, you are actively reconstructing it, which means the memory subtly changes each time you recall it.
So every time you access a memory, you're also editing it.
You're updating it, potentially blurring the line between what really happened and what you now believe happened.
And this whole process relies on shortcuts, which can lead to some strange phenomena like synesthesia.
Synesthesia is where stimulating one sense automatically triggers another, like seeing colors when you hear sounds or even tasting words.
It must be so strange.
It points to the brain's massive interconnectedness. And related to that, the brain uses heuristics, mental shortcuts, that are normally helpful for making quick decisions, but are also responsible for all the common biases and illusions we experience.
And one of the most relatable of these phenomena is the voice in your head. Is that real?
Well, when you think in language, that voice in your head uses some of the same brain areas as actual speaking and listening. And similarly, when you read dialogue in a book, the parts of your brain related to hearing speech actually activate, as if you're faintly hearing the characters talk.
Let's talk about the most powerful sense for unlocking those memories, smell.
Smell is the sense most strongly linked to memory. That's why a single scent can bring back these incredibly vivid moments from years and years ago.
Why is that?
It's because the olfactory bulb, where smells are processed, is directly connected to the brain regions involved in emotion and memory formation, like the amygdala and hippocampus. It's a direct line to your past.
Our evolutionary wiring also explains why modern life can feel so stressful.
Humans are wired to notice threats and negative information more than neutral or positive things. It's a negativity bias.
A survival feature.
An essential survival feature when we needed to spot a predator in the grass. But in the modern information age, that same bias can easily backfire and contribute to anxiety.
And we can't forget the power of belief. The placebo effect.
The placebo effect isn't just in your head. Believing a treatment will work can trigger real, measurable changes in your brain and body, including the release of your body's natural painkillers. It's the incredible, measurable power of expectation over physiology.
And one final, massive, cosmic fact about yourself. The static on an old TV screen.
Roughly 1% of that static, that tiny snowy fuzz of noise, is leftover electromagnetic radiation from the Big Bang.
You're kidding.
Not at all. In a very literal sense, when you looked at that static, you were seeing the faint, ancient afterglow of the birth of the universe.
We've completed our tour of the natural world and the internal self. Now we're moving on to how humanity has shaped and documented the world, looking at the surprising connections between our ancient past and our cutting-edge future.
And let's start with a foundational moment in computing history and the origin of a word we all use.
The first computer bug was a literal bug.
It was a moth. It was found trapped in a relay of an early electromechanical computer, causing it to malfunction. The term bug has stuck ever since.
And the word robot itself has a surprisingly depressing origin.
It does. It comes from a Czech word, robota, which means forced labor or drudgery. It was first used in a play from 1920, and it reflects those early anxieties about automatons being designed solely for relentless, grueling work.
And the pace of progress since that play was written has just been staggering.
There have been more fundamental shifts in human communication tech in the last 150 years, from the telegraph to the internet to AI, than in the tens of thousands of years that came before that.
We are living through an unprecedented acceleration.
And this acceleration is built on components that are so small they're basically invisible.
You're talking about transistors.
Consider the microscopic scale of computing. There are now more transistors in the world today, those tiny little switches running our electronics, than there are leaves on all the trees on Earth.
I can't even process that scale.
And the power we carry around in our pockets just puts the past to shame.
Smartphone.
The modern smartphone in your pocket has more raw computing power than NASA used to land people on the moon during the Apollo era.
The entire program.
It highlights not just miniaturization, but the explosion of accessible power.
But not all modern technology beats the ancients. The Romans, for example, were master builders.
Their concrete structures have survived for 2,000 years. And part of the reason is that the volcanic ash they use in the mix actually reacts with seawater to make the concrete stronger over time.
So it self-heals, in a way. Modern concrete doesn't do that.
It often doesn't have that longevity, no.
And while our modern world is defined by this constant connectivity and speed, people in the 19th century were worried about what we'd now consider trivial speeds.
Right. In the 19th century, some doctors genuinely worried that people would be overwhelmed or even driven mad by the sheer speed of traveling on trains.
And how fast were they going?
About 30 kilometers per hour. It just shows how radically our physiological and psychological adaptation to speed has changed.
Okay, a modern myth that needs debunking. The QWERTY keyboard.
The QWERTY layout wasn't designed to slow typists down, which is the popular myth. It was actually designed to separate common letter pairs to prevent the mechanical arms of early typewriters from jamming when people typed too fast.
So it was a solution to a mechanical problem, not a human one.
Exactly.
Speaking of things we will never fully map, let's talk about chess.
The number of possible games of chess is larger than the number of atoms in the observable universe.
That's another one of those brain-breaking facts.
We will never map all the possible pathways or scenarios. It just demonstrates the explosive power of combinatorial mathematics.
And finally, let's look at a strange biological interaction with fire.
There's a species of mushroom nicknamed the zombie fire fungus.
The what?
The zombie fire fungus. It can lie dormant for years and years in burned forests, just waiting, and then it bursts into life when conditions improve. It's a biological adaptation to the cycle of forest fires. It survives the destruction to thrive in the aftermath.
And a quick note on infrastructure. We often think the internet is just floating around in the air.
Satellites play a role, but the vast majority of our global data is physically carried by undersea fiber optic cables stretching across ocean floors connecting the continents.
So it's mostly physical deep-sea pipelines.
Exactly. And sometimes our most valuable data is kept on the oldest tech.
What do you mean?
Some of the world's most valuable, high-volume data is still stored on reels of magnetic tape, a technology older than many of the people using it.
Why?
Because tape remains incredibly reliable and cost-effective for long-term archiving. It proves that older technology isn't always obsolete.
Okay, we've reached our final chapter. This is where we confront the facts that challenge our fundamental understanding of physics, proximity, and even our own self. These are the pure mind benders.
And let's start with a big one that affects every single interaction you have.
You never, ever actually touch anything.
Technically, no. We mentioned it before, but what you feel as touch is the electromagnetic repulsion between the electrons in your atoms and the electrons in the object you are supposedly touching. There is always a tiny electromagnetic gap.
You're always hovering just above the surface.
Precisely.
Now, a fact about deep time and our shared history. Every single breath you take.
Every breath you take likely contains at least one molecule that once passed through the lungs of every single person who has ever lived.
Profound.
It is. It's thanks to the continuous mixing and cycling of the Earth's atmosphere over millennia. It's an incredible illustration of how interconnected we are to the entire history of humanity.
To bring us back to scale, let's use that football analogy for the solar system.
Right. If the sun were scaled down to the size of a football, the Earth would be the size of a peppercorn, several meters away.
It just helps visualize how much empty space there is even in our own relatively compact system.
And at the very smallest scale, down in the quantum realm, reality itself seems unstable.
What do you mean by that?
At the quantum level, particles behave both like waves and like particles at the same time, and their properties aren't fully real until they're measured.
So the act of observing it changes the outcome.
It fundamentally changes the system, yeah. It suggests that reality is probabilistic until we interact with it.
Okay, let's talk about gravity and time, which are far more flexible than we imagine.
Time actually passes slightly faster for you on a mountain than it does at sea level. Because the higher you go, the slightly weaker gravity becomes. And according to Einstein's theory of relativity, less gravity means time speeds up. It's an effect that we can measure with precise atomic clocks.
And even when you just look in a mirror, you're experiencing the past.
A tiny fraction of it, yes.
Right.
You're seeing yourself a few nanoseconds in the past because light takes time to travel from your face to the mirror and then back to your eyes. You are always playing catch-up with your own reflection.
And finally, a fact that reorients us in the universe. The whole concept of up.
The direction you think of as up is simply away from the local center of gravity. There is no universal up in the universe. If you were floating in deep space, the concept of up would cease to exist entirely. It's a purely localized, relative idea.
Let's end with a look at language and consciousness. The word monster used to mean something very different.
It used to simply mean something remarkable or strange. Only later did it evolve to take on a purely negative, frightening meaning. And that linguistic shift kind of reflects a societal tendency to view the unknown or the anomalous as inherently threatening.
But despite those anxieties, our generation has experienced something completely unique in human history.
People alive today have lived through more fundamental information and technological changes, from rotary phones and black and white TV to global AI networks, than any humans who came before them.
We are uniquely positioned at the steepest part of the curve of technological change.
And as you process all of these incredible, bizarre facts, just remember the final mind bender, the feeling of being you right now.
What do you mean?
Well, right now, billions of your neurons are firing in these precise electrochemical patterns, turning electrical spikes into the subjective experience of consciousness.
The feeling of me following a story.
Exactly. The feeling of you following a story, processing abstract concepts, and internalizing all these new realities. So we've raced through cosmic collisions, diamond ring, blue-blooded octopuses, and the fact that we're mostly just empty space held together by repulsion. The diversity and sheer volume of these facts really confirms our theme, doesn't it?
It really does.
Common sense is usually the first casualty when you start dealing with the universe or deep time or even the microscopic parts of your own body.
It's the ultimate feeling of, I thought I knew the world, but I really didn't. We found out that trees communicate, that ants build living bridges, and the power of a smartphone is greater than what took us to the moon. Every single layer of reality, from the quantum vacuum to the Great Barrier Reef, just hides this profound strangeness.
And that strangeness forces us to constantly update our model of reality. We mentioned earlier that memory isn't a recording, it's a reconstruction. It subtly changes every time we recall an event, often incorporating new information.
So we want to leave you with this final provocative thought to mull over. If your brain is constantly rebuilding the past based on new data and new information, like everything you just heard today, how confident can you be that the reality you experienced yesterday is exactly the same as the reality you remember today?
Explore what new facts might change your internal model next. Thank you for taking this brain binge with us.
We'll see you next time for the deep dive.
That's it for this episode of Brain Binge. If you enjoyed getting your mind twisted tonight, do me a favor, comment, like, and subscribe so you don't miss the next deep dive. Got a weird fact, mystery, or place you want an episode about? Drop it in the comments. I read as many as I can, and I'm always hunting for new ideas. Thanks for listening, and thanks for letting your brain binge with me for a while. Stay well, stay curious, and I'll see you in the next one.